Um, Hello, everyone. We are here today. My name is Thomas Rini. I'm here today with my colleague Ole Carstensen.
Hello.
We are both from SCM, the Software for Chemistry and Materials. And we have a special guest today, that's Harry. And yeah, today we're going to talk about Ligand Field DFT. So Harry, if you could say hi.
Hi, hi everyone. So very happy to be here today and to present Ligand Field and density functional theory.
So yeah, if you could give us a brief idea, what are we going to see today? Just an overview.
So let's start then with a short presentation. So it will be some theoretical part. So I'm Ari Ramanantoina. So I'm from Madagascar, but I'm here in Switzerland. I did my PhD in Switzerland in Fribourg, and I did also a postdoc in Switzerland in Villingen. And now I'm working for myself, let's say, for a short period. And I would like to present then this Ligand field density functional theory. And I will propose together with people from SCM two examples, so two tutorials of calculation of the ground state of uranocene, which is an actinide compound which contains uranium 4+, 5F2 electron configuration. And then we jump to X-ray absorption spectroscopy calculation. So it will be manganese transition metal compounds. And yeah. What is basically LFDFT? So LFDFT allows to quantify physical properties, so in principle optical, but also magnetic, in terms of intuitive and well understood parameters, which are Slater-Condon parameters, spin-orbit coupling, and Ligand field potential. And it is specific only for open shell systems, so metal-based compounds, so metal coordination compounds, with transition metal, lanthanide, and actinide. And it works only on the subspace of the open shell electron configuration. For instance, if you have transition metal and you have electrons in the d orbitals, then you have this 3D open shell configuration. So all the closed shell effects are simply neglected. So I take here as example uranocene. So uranocene, as I said before, is an uranium compound which is surrounded by two ligands. So the ligands are this C8H8 2-, and the uranium has formally a charge of +4. When you do a DFT calculation of uranocene, then you end up with this IMO diagram, where you can realize that some of them, these IMOs, has merely atomic character. So you can see here, for instance, the 7 IMOs which arise from the 5F orbitals of the uranium center. Then, by doing Mulliken population analysis, then we see that it has more than 70% of the uranium 5F characters. So they are what we can use. They can be used for the LFDFT calculation. So the Ligand field theory is actually a model Hamiltonian, an effective Hamiltonian theory, where the Hamiltonian is set up according to the electron repulsion in blue here in the equation, then the spin-orbit coupling in green, and then Ligand field potential in orange. So in principle, when you diagonalize the effective Hamiltonian, then you will end up with multiplet energy levels, which is given here as E, and then the phi, which is the multi-electronic eigenfunction. So inter-electron repulsion and spin-orbit coupling. So the inter-electron repulsion is a 2-electron operator, so it is composed in this way by Slater-Condon parameters, which is a reduced matrix element here, and then an angular part, which is here. And then we have again another terms according to the electron configuration system in which we are working. And then the spin orbit is also defined in a similar way, but only that it is a 1-electron operator, or you have again a spin orbit coupling constant, and then an angular part, which is defined here as L times S. So the Ligand field is defined in terms of a Poisson equation here, as you can see here. So R is the coordinate of the ligand and R is the electron. Then we can expand it in terms of Legendre polynomials, and we end up with a matrix element, as you can see here, HLF, which is also a product between a reduced matrix element, which is the parameters P, as you can see here, and then again an angular part, which are here. So in principle, in LFDFT, we will try to obtain these parameters. So the Slater condon, if I just go back to the slide, so the Slater condon FK parameters, then the spin orbit coupling constant, and then these P parameters, and then from these parameters we can set up the Ligand field Hamiltonian and get the multiplet energies and the electronic eigenfunctions. Yeah. So now we can probably jump to the tutorials. So I will show you two examples of LFDFT calculation. So first is actinide compound, uranocene. So we are going to calculate the ground state and the low-lying excited state of uranocene, which arises from 5F2 uranium electron configuration. And then later on, we will go to the L2-3 X-ray absorption application. Then I need to import the Cartesian coordinates. So import coordinates. And in import coordinates, so I go to desktop, uranocene, then the site matrix here. Okay. So you can see here the coordinate of uranocene. So it has high symmetrical point groups, D8H, as you can see here. So the two ligands are arranged in this way. And the uranium is in the center. So the first step is to define the ADF calculation. So the task is single point, and total charge is 0 in this kind of compound. Then extended functional. So let's go for GGA functional, for instance, PD. Then relativity, so scalar basis set. So in principle, triple zeta basis set is good. And then frozen core known, and numerical quality is normal. This is fine. Okay, so we have defined the IDF parameters setup, let's say, and then we go to details. And in details, we have to define the symmetry, and in LFDFT, the symmetry has to be no-sim. It works only for no-sim, so you have to set up no-sim in this way. And we have also to go to user input to set up occupation. Okay, so okay, so here is the occupation. So you have A202, and then we have these 5F occupations, which are 7 times 2/7, as you can see here. And this is actually the molecular orbitals indices. So for instance, this 202 electrons is in IMO 101, and then the first 5F electrons will be in IMO number 102, and then so on and so forth till 108. So now we can go to Ligand Field DFT and then define the IMO indices. So as I said, so it starts from 102 to 108. So 2, 3, 4, 5, 6, 7, 8. So N value is 5 because it's 5F electrons, and L value is 3 because it's F electrons. So Sora is for the spin orbit, and then we include spin orbits coupling, so you put 1 for the scaling factor. Now we can run the calculation. So save. Yes, and we run it. So we open log file then. But now we are still in the ADF calculation. It might take some time, let's say 2-3 minutes perhaps.
We'll probably cut this out then.
Yeah, or we do fast forward.
Okay, yes. Oh. I guess it's more or less fine. It has
Switched.
19 cycles, and we are waiting for the next output. Yes, so the warning is okay because we have occupied the molecular orbitals with partial electrons, partial occupied orbitals, so it's fine for the 5f orbitals of the uranium.
This is now the part where it actually does the LFDFT.
Yeah, but the LFDFT will be also very fast. As soon as we get the ADF calculation, the LFDFT is very, very fast.
Okay.
We will see then. Okay, now it's fine.
Okay, here we go.
And then also LFDFT, so it is now over. So we can then now go to, oh, here. Now go to the ADF here, to the ADF job, and to the output first. So you can see here the Cartesian coordinates and all the DFT calculation. If you can just go down there and see the molecular orbitals. So our interest is mainly MO number 102, 103 till 108. So let's go there. Check here. So you see here the molecular orbitals that are occupied with fractional electrons, and you see 102 from 102 to 108, and they are mainly about 5f character of uranium. And you can see, for instance, the first one is about 75 5y, and then 30% 5 wakes, and here, for instance, 107 is like 73% fxyz, and here you have nearly atomic character, 95%, let's say. And here also, I've said, and so on and so forth. And we can also go to the LFDFT result. So the LFDFT result is at the end of output file. So now we have here parameters, so the latter common parameters, which have been calculated from the DFT calculation. Then the spin orbit coupling constant, which is also calculated from the DFT calculation. And here you have the list of the multiplet energy levels. So you can see, for instance, that the ground state of uranocene is about 2-fold generate because the multiplicity is 2, and this is level number 1. The energy is 0, so it's the ground state. So here we have expectation value of SL and J, and SL is not a good quantum number because of the Ligand field. So J is a good quantum number because we have axial symmetry. And here the J square is 9, so the ground state of uranocene has a J of 3, and it is a doubly degenerate. And then the first excited state, the low-lying excited state, is also doubly degenerate, as you can see here with multiplet 2. And J with J equal 2. And here you have J equal 4. 4 times 4 is 16, and this is because of numerical precision of the calculation. It did not reach 16. Then 0, 1, and so on and so forth. And we have also here a spectral term analysis. So you can see that level number 1, which is the ground state of uranocene, we discussed before, is about 82% triplet H and 4% triplet F. And we have also here mixing with a singlet because of the spin orbit coupling interaction. So 12% singlet J and so on. And here we have all the levels, all the spectral term analysis. Yes.
Nice.
So this is basically the uranocene tutorial. Now we can go to XANES application, X-ray absorption spectroscopy application. Okay, so let's start with manganese application. Let's start with X-ray absorption spectroscopy application. So we still need to import coordinates, and the coordinate is in the desktop, and it is here. Open. Yes. So in in principle, it is a manganese atom here, a manganese 2+ ion here, surrounded by 6 water molecule. The symmetry is also high because it has a TH symmetry. And the distances between manganese and oxygen is about 2.2 angstrom. And it was been optimized by DFT, I guess. Yes. But here is the coordinates. So now we have to set up the DFT calculation. So we go again to main. So it's single point. So since manganese has 2+ charge and water molecule is not charged, so the total charge is +2. Then we can say LTA is fine as you wish, and relativity is scalar. And let's go for triple zeta again, and then frozen core is known, and numericality is normal. It is okay. Oh. Okay. I probably need to make full screen of this. Perhaps it's better, and then go to details. Then to set up symmetry, and symmetry is nosin for the Ligand Field DFT calculation. And then we go to the user input here and set up again the occupation. So here I have occupations. And so in principle, we have manganese, H2O, 6, 2+, and some similar operation as before. So your manganese has about 25 electrons. And then we have hydrogen, which is about 1 electron multiplied by 12 because H2O times 6, so 12. And then you have 8 electrons for the oxygen multiplied by 6. And then you have a charge of +2, so you have to subtract 2 electrons, so you have -2 here. And at the end of the day, we get 25 plus 12 plus 48 -2, so we end up with 283. It is okay, right? Yeah. But manganese 2+ is a 3d 5 electrons, so in principle you have 5 electrons occupying the 3d orbitals. So we have occupation at the end of the day of 78 and 5, which is on the 3d orbitals. So the occupation will be A 78 and then 5, which has to be divided into 5 because we have 5 3D orbitals. So we have 1.0, 0, 1.0, 0, and 1.0 like this. So 5 times 1.0 and 78. And then just to show you again that this IMO is IMO number, here, IMO number 39, and then the next IMO, which is about 3D, is IMO number 40, 41, 42, 43, 44. You can see here. Yeah.
Yes.
So now the Iraq occupation is set up, so we go to the LFDFT. LFDFT here. So the MO is then 40, 41, 42, 43, 44, 44. And L value is 3, L is 2, 3d orbitals, SORA, and then spin orbit is activated. And now we can save. Call it manganese is ground state. Okay, save. Okay. Something which important in calculation in a spectroscopy, X-ray absorption spectroscopy calculation is to go to details and to specify in the output details that we want all the orbital printed, so we can see what the core electrons from where we are going to take 1 electron to excite 1 electron. Yeah. So now I need again to save. Yes, and now we can run the calculation. It is supposed to be here. It is here. And we can open the log file. Yes, so it starts here, the SF cycle. Might take 1-2 minutes. Okay, so now it is done. Yes, and so we'll open again output file. So here, so output file is here. So here it's again a calculation. So manganese with water ligands, and we can go to the IMO list just to see our active orbitals, and our active orbitals are here. So number 40 to 44, and you can see that it is merely 3D of the manganese with 88% here, and here you have 75%. And here are the energies, so it is perfect. And we can go now to the LFDFT result. So it is at the end of the output file. And here we have, again, the Slater Condon parameters, which are calculated from the DFT calculation. And here is the spin-orbit coupling calculated from the DFT calculation too. And here are the multiplet levels. So the ground state is this 6-fold degenerate, which is 60, which in principle it is split by zerofield splitting into very, very small energy splitting. But here energy is very, very small, so it is not counted here in the output file. And here is again the S2, L2, and G2 value. And here you have then tablet grammars, and there are some 4-fold degenerate because it has a high symmetry, as I said before. So it has a TH point group. So here you can see all the energy levels, and again the spectral thermanalysis. So the first level, which we discussed before, is about 6-fold degenerate, is 99% sextet S, and it is mixed a little bit with 48J and 48P because of a spin-orbit coupling interaction, as you can see here, and so on and so forth. Now, to do the XI spectroscopy calculation, namely to calculate this L2FH. L2FH means that we have to promote one electron from the core 2p orbitals to the valence 3D, and to calculate the spectral profiles that we obtain from this electronic transition. So we need to localize where are the 2p orbitals of manganese. So let's just go back to this molecular orbital list. And now it is not yet, since we printed all the IMOs, we have many IMOs here, but here, okay. So here we have 1s of manganese at this energy, and then the 2s of manganese at this energy, and now we have the P of manganese, which are here. So it's the IMO number 3, 4, and 5. So it is formally with 6 electrons, because 2 plus 2 plus 2 equals 6. But now we have to promote one electron from these orbitals to the 3D of manganese. So it will be occupied by 5 divided by 3 each in the next calculation step. So let's set up these new calculations. 3, 4, 5, yes. So we go back again to the RDF input here, and then go to the details, user input. So here is our our occupation before for the ground state calculation, and now for the excited states. We do A, and we say that it's IMO number 3, 4, 5 as about 2p orbitals of manganese. So in principle, we have 1s of manganese, which is about 2 electrons occupying the 1s, and then the 2s. And then we have 3, 4, 5, which is the 2p orbitals. So in principle, this has about 10 electrons. So you have to subtract these 10 electrons from the 78 before. So we end up with 68 here. And again, with the same occupation for the 3D. of the manganese, but then we have 1 electron more in the manganese, so we put 1 electron more, which is divided by 5, so we get 0.2, so we have 1.2 at the end of the day. Okay, so now for the 2p, you have 5 over 6. 5 over 3. And now I just need to, let's say I just copy it from here and buffer. For the 2p, we have this occupation 5 over 3 for each 2p orbitals, 68, and then the 3d, and we can then decomment this command, and we go to File and Save As, and we call it manganese excited configuration, ES. Yes, save. Okay, so now we need also to set up LFDFT then. Here. So this is now, we have now 2p, which is open shell, and 3d open shell. So let's transfer this to the IMO shell number 2. So here is still 3, 2, Zora 1, and the first one will be the 2p orbitals, and these are IMO number 3, 4, and 5, and this is 2p and value equal 2 and value equal 1, Zora and 1. And we will do the excitation from the ground state, which is the result of the former DFT calculation on manganese, which is manganese ground state, as you can see here. Put it there. Then save again. Okay. So now things are more or less good. So now we can run calculation. Yeah, and let's open again log file. Yes. It might take some time, 2-3 minutes too. Okay, so now it is done. Now let's go again to the output file. So here. So the same input as before for the DFT calculation, and we go again to the list of molecular orbitals just to see our active orbitals. We see here again the manganese 3d orbitals, which is occupied with 1.2 electrons each, so it's 6 electrons in total. You can see here from 40 to 44. And then we can also see here the 2p orbitals of manganese, which is MO number 3, 4, 5, and they are occupied with 5 over 3 electrons, so 167, as you can see here, so 3, 4, 5. And now we can go to the LFDFT results. Yeah, you have all these spectral terms analysis, let's say. Yeah, it's here. So we start again with first, this is not the ground state, this is the lowest energy of origin from this 2p5 and 3d 6 electron configuration of manganese. You can see here. And so you have again Kramer's tablet, as you can see 2, 2, and 4. We have 4 degeneracy because of the TH symmetry of the molecules, let's say. And here you have all the multi-rate energies of manganese in this context. And here is again the spectral terms analysis, you can see here. And we have also at the end of output file here, oscillator strength calculation. So in principle, you calculate the oscillator strength from the ground state of uranocene, which before we described this six-state, multiplicity 6 state, and then calculate the electric dipole transitions from this state to the whole manifold of the 2p5 3d6 electron configurations, as you can see here in this electron transition problem. And we got here the oscillator strength, which we are going to visualize using the IDF spectra later on. Okay, so let's go to ADF spectra. So spectra is here. Then file open. And the folder was in desktop and manganese, and it was the excited configuration here. And we open it. So here we have the Ligand Field DFT energies, and we can also go to the Ligand Field DFT excitations. You can see here. And here we have X-ray absorption spectra of manganese in water coordination. Here you have first peak is corresponding to the L3 edge and then the L2 edge. And this is separated by this energy gap because of the spin orbit coupling of the 2p electrons is quite high. And here we have also a table of energy levels with oscillator strength and also all the necessary information that is needed for this calculation.